Hello everyone, and welcome to me talking about Ethereum networking and DevP2P. I've got a few people that are going to be sitting in my audience and heckling and giving questions and correcting me, so hopefully this will be a useful way of doing this, and we'll have a good video for you to watch, which talks through how the Dev2P networking happens in Ethereum. And as I start, I want to start by just giving a call out and special thanks to Raul Kupalani, who did a lot of work in the Pegasus and Pantheon codebase on the Dev2P layer and has given me a lot of feedback on these slides. So pretty much everything that is right comes from Raul. Everything that is wrong is my interpretation of things and my reading. So to start off with, this is a tale of two stacks. Looking at the way that the networking happens in Dev2P is there's two things that are happening, two stacks that are happening kind of at the same time. So there's a discovery sort of set of networking that's happening over UDP, and then the more kind of core day-to-day networking, and once you've actually discovered nodes, that's happening over TCP IP. Or just TCP. So I'm going to go through each of these two stacks, starting with the discovery. So the discovery is what's used to build the peer-to-peer network, and it's a Kademlia-based protocol. Kademlia being a paper and a well-defined distributed hash table sort of protocol. And Kademlia also being used by BitTorrent and the mainline DHT. So I guess the reason that Kademlia was used by Ethereum is because it is that well-defined standard and well-defined protocol. So Kademlia, as I was saying, is a peer-to-peer protocol. Has two parts as a part of the Kademlia protocol: node lookup and a distributed hash table. The node lookup part is what specifies the structure of the network. It's the routing table, which says how you can sort of communicate and reach other nodes inside the network. The distributed hash table is a key value store. Kademlia runs over UDP as its communication sort of layer and networking, and it's specified in the paper that's linked to there. And so you can Google Kademlia and you'll end up with the paper that talks about it. So one of the important things when thinking about Kademlia in terms of Ethereum is that it uses the routing table part. We don't actually use the key value store part of Kademlia in Ethereum. So the routing table, that's the table that's divided into buckets, where each bucket holds nodes at a distance from the current node. The distance of nodes is not actually related to how close they are in the network at all. It's related to just I guess, trying to spread things out and getting a wide coverage of things. So does an XOR of node IDs, which is then in Ethereum, a node ID ends up being a public key. So that's kind of a pretty random number. And then to make it even more random, they do a KEKAK hash of that node ID. So just that sort of note that the KEKAK hash is a very similar to SHA-3 hash, but it was kind of specified before the SHA-3 standard was created. So the KEKAK SHA-3 is based off of the KEKAK function, but the KEKAK hashing function that is used in Ethereum will produce slightly different hashes to what you get if you SHA-3'd the same bytes. So Kademlia has 4 messages that can be sent out with responses. So the ping, find a node, a store, and find value. And so the ping and find node messages they have corresponding things in Dev P2P, and the store and find value messages are very much related to the distributed hash table, and so they are not implemented inside of Ethereum. So Kademlia, when you're bootstrapping and you want to join a network, you connect to a bootstrap node, you send a find node request of yourself, and whenever you do a find node of yourself, or send out a find node request, as a part of that message, you'll send out the node ID that you're finding, and you'll get back a response of all the neighbors to that node. And so that find node is actually in much of the literature around Ethereum, it ends up being called find neighbors. And I think kind of find neighbors is almost a better term because that's more indicative of what it's doing. And then as a part of that bootstrapping, you'll refresh your buckets by looking up a random value, and then that will sort of go through the nodes, and you'll get some data. So how this Kademlia stuff is implemented in Ethereum. So as I mentioned, there's the ping and find node messages are the ones that are implemented. So a ping in Ethereum has a Pong response, and the find node gets translated to being that find neighbors method. At least that's kind of what most of the clients end up calling it. And then it doesn't implement the distributed hash table part, so it doesn't have a store or a find value. So there's that, again, those two sets of paired messages that we've been talking about. The ping, which gives a Pong, you get a Pong response back to. You find neighbors, which you get back a list of the neighbors. One of the things there's a few things that are different, or I guess particular to Ethereum. And so one is that all messages are signed with the node private key, which starts to be interesting as well then, because there's this concept of bonding which is implemented. And so before responding to any of those find neighbors calls, you need to have bonded with a node. And that was implemented in response to a denial of service, a distributed denial of service attack that was made against the Ethereum network. And so that's why they thought, okay, yep, we'll solve that, we'll implement this bonding sort of process. There's questions about whether that was actually the most effective thing to have been done, but it is what it is, and it is there now. So the idea with the bonding is that before, and as I was saying, it's before you respond to a find neighbors, you need to have done a ping and a pong pair of messages. So what do the messages look like? So the first thing is that there's just a simple sort of structure. It's got a type, some data, elliptic curve signature of the type and data, and then a hash of that signature, the type and the data. So the ping message, again, it's used to initiate the bonding process. The data that it contains is who you're sending the ping from, who you're sending the to, bit to, and an expiry. And then in response to that ping message being sent, you get the pong back, so classic ping pong. In the pong, it responds with the ping hash. So when you perform a ping, you should store a hash of that ping message, so that when you get a pong back, you can kind of confirm that, yep, that pong is a pong that's valid for a ping that I've sent. Yep, so the machine that sent the ping will bond on the receipt of the pong if the ping hash matches. So the find neighbors message is going to a node and saying, give me a list of the neighbors that you know about for a given node, which might be a completely different node. As a part of that, what you send is the target node that you want to look up the information, the set of neighbors for, and an expiry. So as we've mentioned before, if the source so if someone is sending a find neighbors to you and you receive it and you have not bonded to that node, then drop the message is the way the protocol works. If you are bonded with each other, then respond with a list of the neighbors that are closest to the target node that was provided in that message. So the data that is included in that neighbors response is a list of peers to the target node and an expiration. So once you receive the list of neighbors, typically what you'll do then is want to do a ping pong bonding process with each of those nodes, so that you can start to sort of spread out and expand your network to include people. So the Bootstrap process, using this discovery protocol in Ethereum, is to first connect to the boot nodes, then to bond to them, and then to do the find neighbors. So an interesting side effect of that is that, or an interesting thing to note, is that the list of boot nodes is actually currently hard-coded inside the client. And so in the public sort of Ethereum world, there's actually about 5 different boot nodes that are sitting there that are actually really sort of a bit of a centralization point to our decentralized network, because that's where everyone goes when they're starting up their clients for the first time. That's mitigated a bit by the fact that the node table is persisted. So people, every time you start your client from scratch, you're not actually going out to the boot nodes, but the first time that you ever started up, you will be going out to those boot nodes. So you've got this table that you're keeping of the network and sort of maintaining this list of who the neighbors are and your distances from them. You want to keep that up to date, and so periodically you'll go through and do a refresh. And so this refresh period is a configurable option on clients. Sort of ranges from, for some clients, maybe the defaults I think are about 5 minutes, and then for other clients the defaults are more like a day. Okay, so some more of the differences then between the way that DevP2P does its discovery versus Kademlia. The ping pong bonding process that we talked about to prevent the DDoS, the way that they compute the distance, so whether it uses the most significant bit or the least significant bit. And then the other thing is that the Kademlia paper talks about the reputation of nodes being narrowed down to being very much about how long a node has been connected. Within DevP2P, it's actually left up to the clients to think about reputation, but it is hinted that it should be a bit more sophisticated. But then pragmatically, it's actually probably not really that sophisticated in most clients. So that's our discovery protocol, which again runs on top of UDP. So the second stack that we've got then is the DevP2P sort of more runtime communications for how more things are working once you've discovered nodes. How do you actually want to send messages to those nodes? So it's a protocol that sits on top of TCP, based on top of, then I guess it's a network stack, which when you do it in a diagram, it looks all beautiful, but in reality, it ends up being a bit more smeared between the different layers, because that's the way people end up seeming to write code and actually not really getting the messages quite right. And probably actually more than how people write code, but how the protocol really works. So there's probably a bit too much the abstractions are a little bit leaky between the layers, I guess is probably the way to sum it up. But if you look at it at a sort of ideal sense, you can say, okay, there's the RLPx is the sort of underlying protocol which helps do the multicasting and has the underlying sort of protocol that's sitting there. On top of that, there's a wire protocol, which is sort of pretty well defined for how some of the messages and things get initiated. And then there's the subprotocols, which is the actual almost userland type protocols that are having messages sent around. So the key one there is the ETH subprotocol, because that's the one that has like the Ethereum blocks and transactions and how things get passed around the network.
So Rob, to interrupt for a second, looking at the IBFT stuff, I'm assuming that appears as a sub-protocol there.
So it should. I don't think they've currently implemented it as a sub-protocol. I think they've kind of forked the ETH sub-protocol. But it makes a lot of sense for there to be a IBFT sub-protocol.
Right.
With the caveat that's going to have some sort of funky name, because the sub-protocol needs to have a 3-character name.
Yeah, I'm lost.
Okay.
Cool. Thanks.
Yeah. We'll see more. So RLPx provides the encrypted multiplex messaging, which is a fancy way of saying that the messages within RLPx, well, the encrypted part is, each message is encrypted, but the multiplex is just a fancy way of saying each message has at the start a indicator of what type of message it is. So to start with, which protocol it is, so it's going to be that it's the wire protocol, and then after that, the first part is going to be which sub-protocol it is, and then within the sub-protocol is going to start with which type of message it is within that sub-protocol. The key thing that RLPx does is sort of the session initialization, in particular the crypto handshake sort of work to be used within the session, and it provides that message framing work. So the session initialization has 2 parts to it. So it first does a handshake of the crypto, which is very much in the RLPx layer, and then it does a hello messages as a part of the wire protocol. And once you've performed those 2 parts, then you do have a session key that you're able to start to use for sending messages back and forth. And so it does actually, this is part of where the blurring of the layers starts to happen. So you can't actually use RLPx until you've got this wire protocol that's set up that has completed that handshake protocol within the wire protocol. So the session initialization looks like this. So you've got the crypto handshake to start with at the top, or the auth handshake in that diagram, and then there's the wire protocol handshake. So the crypto handshake, the first message as a part of that is an auth. And so the auth message, before sending the auth message, I'm lisping a bit, but before sending the auth message, the initiator of the handshake will generate the secret information and the random information, and then it'll send that message across to the remote. So your initiator sends an auth message across to the remote, and then the remote, on receiving an auth message, will generate an auth-ACK message, creating that ephemeral public key and nonce, and it'll transfer a response then back to the initiator. So on receiving the auth message, the remote now has, and generating those secrets, the auth message, the remote node will have the information it needs to be able to send a hello message. When the initiator receives that auth-ACK message, it will then also have all the information that the remote has, and will also be able to generate and send the hello message. So that's the second part of the that protocol handshake, is that hello messages that they're able to send back and forth to each other, So each node is able to derive all this sort of secret information based off the information that they've shared with each other. And in doing and sending this hello message, they're initiating the wire protocol. And having received the hello message, they're able to fully authenticate the protocol handshake. Okay. So that's the top and the introduction to the session initialization. And start to do some more details of what's kind of sitting inside those messages. So the hello message contains the protocol version, the client ID, and importantly, then it also includes the list of capability and capability version tuples. So those capabilities are the sub-protocols that are supported by that client. And then it also includes the port and node ID. So that, having sent the hello message, the two clients are then sort of entering into a phase of sub-protocol negotiation and initiation. So the nodes, and the goal of this is to work out what protocols you can use to communicate with each other and what version number to use in doing that communication. So as I mentioned, the hello message, it's including those list of capabilities and capability versions. Then the sub-protocol negotiation is essentially each client taking the responsibility of saying, okay, I will join those two lists together and give me the overlaying or the intersection of the sub-protocols and version numbers to say, this is the negotiation, these are the things that we're going to use to talk to each other with. After picking the highest version for each of those capabilities, it's able to then go through a handshaking process for each of those sub-protocols. And so it does that using, it's sort of defined in the code for the actual sub-protocol itself. And so that's typically then done by sending a status message. And so each node would independently send a status message back to the other node in a similar way to the hello messages done on the wire. Yep.
So does that mean that any given node has got n different versions of n different protocols purely to maximize their connectivity?
Yes, where n in terms of protocols tends to only end up being maybe one or two.
Okay.
And number of versions that they support, again, tends to be one or two.
Okay.
So it's kind of they'll support kind of the latest and maybe back one, but there could be more. But for the most part, particularly running on mainnet, there's maybe two versions of the ETH sub-protocol that are running, and most nodes actually aren't running much more than just ETH. Okay.
Cool.
The issue here that I heard from developers on these clients has been that yeah, you would want to maximize the number of nodes that talk the same language that you do, right? Same protocol and all that. But the problem is, it happens at a completely different layer who you connect to, who you stay connected to. So this distance algorithm and the Kademlia routing tables and the buckets that they use to connect to other peers are completely disconnected from the protocols that they talk to, because what you want to do is to make a network where everybody knows a little bit about everybody else. If you start having a network with specialization where you will only talk to people who talk the same language as you, then very quickly you create islands, right? Yep. To avoid that, the concerns are separated for good reason, but that means that out of the 256 peers you can have maximum, maybe there's a good proportion of them that are completely useless. The only reason you have them in your buckets is because you can keep propagating them to the rest of your network. Otherwise, it would end up being talking to nobody. Which is so. This is a reason for this whole thing. you're having two different layers. One of them is just propagate the number of peers across network, and the other one is to actually talk to them. And you already have conflicts just on that. It's what it is on that.
Yep.
Cool. Yeah.
Cool. Okay, so our wire protocol then has a series of 4 different messages that it supports. So the hello message, disconnect, ping and pong, and they're all actually pretty self-explanatory. So the hello message, that's what we've been talking about in the slides up to date, and so that's used as a part of the session initialization process, and is used to help trigger the negotiation and initiation of the subprotocols. The disconnect is what you use to disconnect from a peer. And when you do a disconnect, you include a single byte reason code where here's the list of reason codes. And I'll test you at the end to see if you remembered this, and I'll move on to the next slide. No, I guess just to say, there's a bunch of different reasons that you might want to disconnect, and it's polite to try and tell people why. Then the ping and pong messages within the wire protocol, which are normal kind of keep alive on here messages. So that's the wire protocol. The next level up, I guess, is the subprotocols. And so I guess the point with the subprotocols is that the DevP2P protocol is extensible and can have these multiple different capabilities or subprotocols that it supports. So there's 4 sort of I've got listed here would be some of the more popular ones that are around, within which the ETH subprotocol is the main one that everyone's going to implement. The live Ethereum subprotocol is a syncing related protocol. Whisper or is another one of the subprotocols, which is used for sending messages to people that you don't want to have these messages written then to the blockchain. And Swarm or is the subprotocol that is used for file sharing. And so these Whisper and Swarm are both probably more experimental subprotocols that are found in Go Ethereum, but probably aren't running in most clients on the network.
So Rob, going to butt in again.
Mm-hmm.
Are there other aspects of the Ethereum client that makes use of Whisper, or is it sort of exposed via the RPC, but otherwise doesn't really have a lot of use?
Yep. So it's exposed via the RPC.
Okay.
The JSON RPC. And so there's people that will build, and so I've heard actually that there's people working on consortium networks inside a consensus that are using Whisper for sending private messages between nodes. Okay, so the ETH subprotocol, there's versions 62 and 63 are the main versions that are sort of out in the wild at the moment. The versions 1 to about the early versions starting at about 1 were sort of some of the experimental versions. And then there was a big jump from maybe about 11 or so to 60. And they just kind of skipped a whole bunch of numbers when they started going sort of live and back into the main network. Version 61 was sort of really being used for a long time, but then was upgraded to use version 62. And so 61 and 62 were definitely running out in parallel for a while. You'll find a lot of the clients that have been implemented today still include the code for version 61 and still loosely involve some support for version 61, but most of them will configure probably, I think, to say, actually, we don't really want to support this anymore. And then version 62 and 63 are sort of the main versions that are supported by most clients. And 63 is a straight additive change over 62. And so the reason that I think most clients support 62 and 63 is because it's cheap and they get to say that they support more. Okay, so the flow of messages is that when you initialize the ETH subprotocol, both nodes will send a status, and then the protocol will sort of continue. You've got connections, and you can sort of do a whole graph of different messages. So here's the full set of messages that are a part of the ETH subprotocol. You can see the version 62 starts with the status, then moves into more blockchain-y things. So you can get block hashes, you can get transactions, you can get headers, and bodies. And then version 63 includes some extra things to try and help with the syncing and pulling data across. So I'll dive into each of these messages now. So the status message is used to inform a peer of its current Ethereum state. So it's providing some of the information about what network ID you're on, the best hash that you've got, and what the genesis hash is. And I'm just going to go pretty quickly through each of these messages. The NewBlockHashes is used to help specify new blocks that have appeared on the network. You should only be announcing the hashes of blocks that have appeared. So this is, I guess, something of this is a message that, say, a miner might send out once it's done some mining work and say, here's some new block hashes world. Everyone see this. So you kind of promiscuously are sending out the new block hashes. And when you're sending out the new block hashes, you should not be including blocks which you've already told people about or that they already know about. And so it's not a script, so it's almost like your RFC style shoulds sort of statements. But if you keep on telling people about blocks that you've already told them about, they're likely to start penalizing you and not treating you as a reliable source anymore. And then that information in square brackets is kind of, and you'll see it across all the slides coming up soon, that's kind of the structure of the message. The transactions message is, again, it's another sort of promiscuous one, and it's specifying some transactions that people should know about. So trying to let people know that here's some new transactions that are coming in. With, again, that sort of rule that you should not be resending the same transaction to appear again. And probably the way that you do it is you'd probably end up with just when you get a transaction that you want to send out, you just look through your list and send that same transaction out to everyone. And you just make sure that you would never resend that same transaction to anyone, rather than just caring about sending it to a same peer again. Okay, the GetBlockHeaders is so those two messages that we looked at first were ones that are sort of promiscuously sent. There's a series then of request response type messages. So like a GetBlockHeaders message is one that you'd send, and then in response you'd expect to have a blockheaders message sent back. So the GetBlockHeaders, like it says, is requiring a peer to send a blockheaders message back. In the request that you send out, you tell it what's the maximum number of headers that I want you to be able to send back. and then some other settings to help sort of either spread out the messages. So you can say with the skip message, say send me every 10th message, every 10th block headers, set of block headers. Or you could use the reverse message to say, okay, I want to go the messages. If you say 0, it's ahead of here, or if it's 1, it's say go backwards. So it's kind of saying how you're going to pivot off of that particular initial block. And then the block headers is going to be the response to the GetBlockHeaders, and it's going to give back a list of block headers as per what a block header looks like in the yellow paper. Similar to the GetBlockHeaders is the GetBlockBodies, and that's wanting to say, give me the actual bodies for these blocks. And you use that specifying the list of hashes that you want to do. So you do like I guess the expected usage would be do a GetBlockHeaders first, and that'll give you the headers, which will include the hashes within those headers. And then you'd grab those hashes and say, give me the bodies. So again, the bodies that are block bodies is the response to the GetBlockBodies message. And unsurprisingly, it's including the list of blocks without the header, because it's expected that you would have already done. The way that you're getting the bodies is you've already said get the block headers first. So new block is another one of the sort of promiscuous type methods that's used to push new blocks out onto the network. So it's not in response to anything, it's just pushing those new blocks out onto the network. So starting to look now at, so that's those messages that we've been looking at are the ones that were in version 62 of the protocol. Now we'll start to look at the ones that are new in version 63. So the first being GetNode Data. And so this is giving you're wanting to look up information about accounts or nodes or states. And then in response, you're going to get the a node data response, which is actually the values, and it's giving the best effort. So it's whatever values you have, you give back. And then the GetReceipts is a similar request where you're saying, okay, I want to give me a collection of receipts, and you're going to get back the transaction receipts for the provided hashes. So those up to there is the set of messages that is a part of the ETH subprotocol. Now I'm just going to quickly cover over from a very high level some of the other subprotocols that are there, and not really get into any more details at all. So you've made it this far. You've made it as far as much of the details are going to get. So the light Ethereum subprotocol has a name of LES and a version of 1. So each of the subprotocols again will have a name, and it's a 3-byte name that's used as a part of the capabilities in the wire protocol when it's going through that subprotocol initiation. Whisper has a name of because, you know, let's be quiet and whisper. There's versions 2, 3, and 5 sort of floating around on the network. And yeah, that's what we've got for Whisper. So again, the Whisper is a way of sending private messages without storing those messages on the blockchain. And Swarm is with the subprotocol name of BZZ and version 0. Well, the version kind of indicates how mature of a protocol this is. And it's used for distributed storage of binary objects. So back to the overview and the two protocols that we've been talking about. So again, there's that discovery, which, as Antoine was saying, the discovery part and the runtime wire protocol are kept quite separate. And so there's not really that information sharing that might help make you be communicating better. And there is that risk of then islands of sub-protocols being kept separate of each other, because there is that discovery phase kept quite separate from the actual wire protocol that's being used for sending messages around. And as I'm looking at my next slides, I'm looking and seeing that they are very much tied to when I did the live presentation. So I think we are at an ending spot, and I can say, is there any questions?
This might not be a problem for here and now, but does this imply that you actually, when you, in your Ethereum client, you have one discovery stack, you actually have you have one protocol stack per peer that you're talking to? If that makes sense.
So you'd be, say again?
So in the P2P network, you must, do you end up with multiple of the wire protocol stacks? One for each of your peers, basically. Because theoretically your sub-protocol sitting on top of them in different versions, and how else do you segregate your data and whatnot? Well,
yes, I guess there probably would be a bit. So things are capped at the 256 sort of nodes that you'd be talking to. So there's a little bit of capping there. Within all the messages that are being sent, it includes version numbers. So you'd need to, okay. I guess you'd need to at least keep within you the state to know which version to send back or how to respond.
Yeah.
That makes sense?
Yeah, absolutely.
Yeah. So there's, I guess you'd maintain some states for each of the different clients that you're communicating with.
Yes, I guess that's what
that means. Yeah.
So one of your clients could be 62, another one could be 63, and you need to keep them separated in the comms chain, but then obviously combined at the world state point of view and the block management point of view.
Yep. Yep.
Yeah, cool.
Okay, cool. I am going to say goodbye to everyone who's watching and end the video.